Hey everyone. So today we're going to start a new series. And what we thought, based on the comments that we've been getting on our prior series, is we would take a small topic and spend more time live designing and coding it in these videos for those that need a little more sort of step by step explanation as we go along. So I don't know how long this series is going to go. We're going to start with the very basics. In this video, we'll cover an overview and create our first two C++ classes. And then we'll expand on that in the further series to approach our objectives and hopefully impart some knowledge around some good concepts and processes as you design your game. So the topic that we chose is how to scale out your AI in your game so that you don't get into a situation where your frames and your game cycle are suffering unnecessarily due to your decisions around AI and how you populate the world. So we're starting with the uh, map that we had built out in our other series, which is largely an empty map. We were using it for building and crafting and a variety of other activities. But we're going to populate this little area and make it a bit more lively with some sort of NPCs and interactable characters around the area. And then we might put a few trash mobs in and around the hills to kind of give you the feel of how this might work. So let's jump into it. So first, the objectives. Right, we want to populate the world with things to see and do, and empty worlds are just not fun, right? But if we throw a bunch of stuff in that world, we'll very quickly find ourselves in a situation where either our frames on the client are dropping because we're trying to animate and show too many things, or our server can't keep up with all of the computations that it needs to do. So we're going to use four basic techniques that we'll explain through the video series. We're going to be creating an AI spawner, and that allows our world to scale by only considering those actors that are relevant for the world. We're going to link that AI spawner to an object pool, which helps us manage our memory and CPU utilization, and we'll dive a little bit into those topics as we get into the object pooler in more detail. And all the way along, we're going to be sort of setting this up for a blueprint to C++ migration. And we'll see a bit of that here in this video, why. But our intent is that we will work in Blueprint and then migrate some of that Blueprint over to C++ as we finalize our design. And then we'll be testing our performance implications throughout the video. So what I thought I'd do first is I'm using Guild Wars as an example because it's a game I'm fairly familiar with and it has a lot of good examples, right? So the first concept to make sure we think about is that not all AI is created the same, but no matter how low or how simple the AI might be in game, it's going to cost resources. And so in this screenshot, we've got two NPCs, one stationary off to the side. They're just sitting sort of in an idle animation loop, and another that's moving back and forth in the screen. And so they both consume some resources. Obviously, the stationary one uses less resources than the one that's moving throughout the world in a defined pattern. But there are all kinds of uses for your AI to bring life into the world, right? So as simple as placing sort of dogs and birds and animals throughout the world to simulate the livelihood of the world, even though no other player might be there. These background actors that I just talked about here on the screenshot that give sort of a life and an energy to a space. Your interactable NPCs that you can interact with for a variety of reasons, and we'll talk about that. And then, of course, the trash mob scenario that I talked about earlier. So, here's an example of sort of non-interactable AI, right? These birds and insects will react to the player coming close to them. They may fly away, but there's really no interaction that the player can have with that AI. But But nonetheless, it's using compute cycles to determine how close is the player, should I flee, when should I return. Those kinds of logics are all running on each of these actors, and they're all taking CPU and memory away from the server. But they actually make the world feel alive, right? They make you feel like there's something happening in and around you, and it's not just this flat, transparent world. So another example I pulled up is there were these 3 or 4 actors that were in a loop. They were attacking each other. They were training. They were performing sort of mundane tasks. But again, they breathed life into the world, right? They might be, a farmer raking a field and then going, moving over to water their cattle. In this case, they were training on a training dummy, and they were each taking their turn attacking the dummy. And it makes the world feel a little more engaging. But they're basically in an infinite loop. Then there's your various interactables, right? So if you think about most games, they have vendors that you can interact with, right? Where you can sell stuff, buy stuff, upgrade things, etc. Right? They have banks and storages, which sometimes are represented by a person representing the bank or the storage unit that you're going to interact with. There's various quest givers and quest participants that are active in the world, right? Someone standing with a quest icon over their head. You run over, you click on them, a dialogue pops up, and you start interacting with a quest. And then there's some that are just sort of there to move the story along, right? So they may have roles throughout the world, and they might move around the world to different locations as your story unfolds. And so these are sort of the interactable actors that are in the world. And then the last one I want to talk about is a little bit about trash mobs, right? And you see a trash mob that is likely associated with an AI spawner if you see the following behavior occur. You get within a certain range of the trash mob, and the trash mob locks on you and attacks. You run away, and you get far enough away from where the incident occurred, and the trash mobs turn around and they return back to their home location. So this notion of when a trash mob interacts with you, but you run away, and then after a certain distance they turn around, they are probably responding to the range around their AI spawner, and they're returning back to a neutral state back. So you'll see that in a lot of games where you can outrun, and they'll obviously disassociate, or they'll just return back to their home base. So those are all examples where I think you see AI spawners in real games. We'll talk about each of those as we go through the series. We'll flesh out our own AI spawner for each of those scenarios. All right, so let's talk about the AI spawner concept. So the notion of an AI spawner, first of all, is that it's a server-only concept. You want all of the interactions around the AI spawner to be happening on the server. And then once the server triggers the logic, we use the net relevant replication to update the various clients. And so the first thing to know about the AI spawner is it is a server-only concept. It doesn't need to be spawned on the clients. The spawners are basically generic actors, so sort of a lightweight actor whose job is to enable and disable more expensive actors. Right? And so the example I've drawn up on screen. If you think about the 3 AIs here, they're all expensive, right? So there are 3 AIs that would be expensive to be running on the server. As the player approaches the trigger point, so as the player starts to enter this sphere, the message will be sent to activate these 3 actors because I'm getting close to the point where they're going to become relevant to me. They're going to become net relevant to me. So as I cross this trigger point, the AI spawner's job is to spawn these 3 actors into the world. And then if I get far enough away, they will be despawned. So the idea is that as a player breaks a zone, the AI spawner initiates these 3 actors. It gets more expensive, But as a player leaves that zone, those three AI actors are decommissioned, and only the simple actor is left remaining. So that enters into an interesting design challenge, which is as the player enters or exits the zone, you don't want your AIs to reset back to default state, right? You want to simulate the notion that they are carrying on their work, even though you're not in the zone. So depending on how long your loop cycle is for your AI, you may have to think about that. If your loop cycle is very short, like just an animated idle state, then you probably don't need to worry about it. But if they have a very complicated pattern of, let's take my farmer example, where they're in the field gathering wheat, and they go to a cow and they feed the cow, and then they go to the barn and they pick up hay or something, and they're in a loop that might take several seconds. You don't want every time you leave the zone and come back into the zone for them to be back at step one, right? So they need a way to be able to continue their pattern even though you're not in the zone. So we'll talk about that later, but it's just something to think about as you go. So the AI spawner is a simple actor. It obviously consumes a lot less resources than the three AI expensive actors. And that's the fundamental principle behind it, an AI spawner. So if you think about that from a map context, right? So now lay out your world where you have multiple AI spawners. So in my example, I've got these AI spawners scattered across my world. And I have two players on the map. Player one is here. Player two is here. So the AI spawner closest to player one will be active because the player is within the range. And both of these will be active for player two. But because player one is not close enough to these, they won't be net relevant for player one. And the same thing is this one won't be net relevant for player two. So for player two, we've got two net relevant zones. And for player one, we have one net relevant zone. And all four of these zones over here are not consuming any resources because no one is in that area. If player two were to move out of this zone towards these zones, these two would deactivate and these four would activate as, of course, they get closer and closer through those zones. So if you think about it from an overall map perspective, if you have hundreds of these on a map, 80% of them being deactivated and only 20% of them being activated, you get a huge performance bump. Now I want to briefly touch on the object pool. So we're not going to do a lot of the object pool early. We'll focus on the AI spawner first because it's easy to hook in an object pool later in the development cycle. But the notion behind an object pool is that you have to recognize it's expensive to spawn an actor into the world from nothing, right? So if I use the spawn actor from class, I need to allocate a bunch of memory. I need to create the object. I need to register it with the engine. I need to do a bunch of startup activities that are taxing. And if I'm spawning and despawning, and on despawn, I have to release the memory, clear it from a bunch of different things. So there's a lot of cost associated with the spawn and despawn activity. Particularly if you're going to do hundreds and hundreds of them, they'll add up and take away your CPU cycles. So rather than spawning or despawning actors, we use a caching mechanism in an object pool. That caching mechanism is I'm going to reset an actor kind of back to its initialized state. So I need a way to reset its variables back to initial state, kind of make it neutral, and put it into the object pool. So that when the next AI spawner needs an object, they will ask the object pool for their AI, and the AI will be handed to them. And so this notion of not spawning and despawning has the advantage of not taking up CPU cycles at critical moments when you need them. But instead, the object pool, is managed from a growth perspective, and it holds those AI actors sort of constant so that we're not dealing with a bunch of spawn and despawn costs. And we'll, as we do some performance testing later, we'll try to simulate some of that to show you the differences between with and without an object pool. So that's a little bit there. Again, we're going to cover that in later chapters. And sort of the last thing to think about is the phasing of how active an actor is. And again, using the circle to represent how far away a player is. If you start down in the most expensive, right, where this sort of orange block at the bottom where an actor is completely active, it's doing all of the things it needs to be doing because the player is within proximity and we want the game to feel interactive, fresh, and alive. But if we start to move away into the yellow circle, we might decide that, hey, after a certain distance away, I really don't need to be animating the actor anymore. The actors, we can turn down the animation cycles and not run as many animations because no one's there to see it. So we start to back away. We get further, the actor gets smaller on screen. We don't need the animations to be running quite as precise as we do when we're up close. Then we get a little further away into the light green zone, and maybe we can start slowing down how reactive the actor is, right? Maybe we can turn down the behavior tree so that rather than constantly scanning and sensing the environment, looking for things, since we know there's no one around it, we can save that CPU performance. And then finally, if we get up to the outer edge of that, we can actually suspend our actor, right? Because there's no one anywhere close, and we can push them off to the cache and suspend them. And so this notion of changing how engaging an actor is, depending on if there's a player within range or not, is a key concept to think through on this video. Now, much of what I've been saying to this point has been about the server and how the server CPU and memory can be managed. There is this notion of net relevancy, which I've touched on, and I'm just going to flash up a couple of things out of the documentation, right? And so one of the beauties of Unreal is that you don't need to do anything in order for the engine to optimize the overall network bandwidth, right? So constantly under the covers, Unreal is determining which actors are relevant for which players. And they're only replicating data to those actors that are relevant to each other. And so there are some parameters and some settings that most people never touch. We will likely end up tweaking some of these eventually. But know that if the server is running and it is the world definition of what is happening, not all clients need to know all of that information. And in which case, some clients will not be given the information until they become relevant. And then the engine has a way of catching up and making sure that they know what all the relevant information is. But this notion of relevancy is important because of the bandwidth constraint between client and server and wanting to make sure that you have low ping, low latency. Unreal is doing 99% of that lifting for you using their net relevancy calculation. They also have a prioritization logic that will load balance how much data is being sent over the network, right? And so each type of actor can be given a relative prioritization rating, right? Those actors that need to replicate more frequently, those actors that can withstand less frequent updates. And so on screen are the defaults, but we're again able to fine tune our prioritization and see the impact it has on our network bandwidth. And so we'll later talk about that as well. But those two are happening kind of behind the scenes. And so kind of just a quick summary on those three, right? So there are three bottlenecks that we need to think about. One, our server CPU and memory usage. That's largely what we've been talking about in this video, which is the use of an AI spawner, the use of object pooling, and then making sure our AI logic is tuned, because all three of those are happening on the server. And if we don't manage the performance, we can run into scaling issues. The second is getting the information from the server to the client. And the great news here is Unreal takes care of 99% of that by their use of net relevancy and replication. And then there's the work on the client, where we have to manage the client's CPU, memory, and in this case, the GPU for the client. Now, the reason I added GPU to the client is the server doesn't render anything, right? There's no, if you're thinking about a server, primarily a dedicated server, none of the meshes are being rendered. And there isn't really a concept of a GPU because nobody is looking at the server. You're looking at it through your client. And in your client, everything has to be rendered. And so one of the biggest areas that you can optimize beyond the static rendering, which is a totally different topic, right? Which is how you define your grass, your trees, your buildings, etc. But the one thing you can do in your AI is the anim blueprints and how much cycles you're using and how much GPU you're using to draw your AI in the game. And so we're going to start heavy on the server CPU management piece. We'll spend most of the video series there. We'll use network bandwidth when we start to fine tune and understand that. And then we'll do some client balancing on primarily the GPU side when we're looking at the anim blueprints. So that's an overview of the video series. Hopefully that sets the context and determines whether or not you want to sort of keep watching the series or not. But there's still nobody in our world. All right. So we now need to, take those theories and those concepts and start transitioning those into a practical way to build out and make this a more vibrant area in the world. And I had said we're going to do this from a perspective of migrating our code to C++ later. So in the last few minutes of this video, what I want to do is set the foundation for how we're going to go through the rest of the videos. And these are my rules that I've learned over the years. My video, my rules. But this seems to work well for me. So the first thing I'm doing when I'm thinking about a new concept like we are here is I'm going to create empty C++ classes. And if I do this because I have in the back of my head that what I'm doing is not going to be long-term sustainable in Blueprint. And eventually some of this code is going to migrate to C++. So that's the very first thing I decide. Okay, what base classes do I need? Are they eventually going to become C++? If so, I'm going to go ahead and create those base classes now. The second thing I try to do is define any enums and structures and variables in C++. It is far easier to do the migration if you do step 2. Now, that doesn't mean I won't create a bunch of Blueprint variables. I will, but I will consciously know that those variables will have to be moved to C++ later, and then they'll have to be rewired up in the Blueprint. And so if at all I can avoid that, I will. In order to think things through when you have a C++ in Blueprint, you kind of need to have a naming convention. So you will see as I go through this series, I might create functions inside of blueprints. I will put a suffix on the end of BP. That's to remind me that this is a function defined in BP. And then when I move it to C++, I'll remove the BP moniker from the back end. And I'll just have the standard function name because that's my end state definition. We'll prototype a lot in blueprints to get it right because it's faster and easier to iterate in the engine. And I would always encourage people to iterate in Blueprint as much as possible. We'll then step back once we get it working. We'll look at our code in Blueprint. We'll make some tweaks and adjustments. And then finally, we'll move that code to C++ when we're happy with it. Now, there are a few exceptions to these, but generally that's the mental flow I go through. You can skip some of the steps if you know you've got a function that you just know you're going to need. Like it's a utility function, and it's easier to just create it in C++ right out of the gate. But for the most part, if you're unsure of where you're headed with a function, I would prototype it in Blueprint first, test it out, make sure it works, and then migrate it over to C++. All right. So we have 2 C++ classes we need to create at this point. The first is our AI spawner. This is the actor that will live in the world, and we'll place them in level at various places where we want them to be in the world. And so you simply go in to your editor. I didn't do this step live, but you go into the editor, you go new, you get a new C++ class, you search for A actor, you then find A actor in the list as the parent class, and then name it. In my case, it's AI spawner. You can name it whatever you like, but this is the actor that will be the spawner in the world. So you go ahead and create that, and it'll create your header file and your C++ file. Then we need to set up for our object pool. Now, I haven't tested this all the way through. I've thought about it on paper. And for this video, we're going to use a uWorld subsystem. So we're going to create a C++ class. Its parent class will be uWorld subsystem. And we'll call it the AI spawner subsystem. Now, I'm doing this because Lyra relies heavily on subsystems. And I thought it would be good to explore the subsystem in parallel to this video series for those that want to understand how subsystems work a little bit more. So it's a bit of a leap of faith. I'm mostly sure that that will work for me as an object pooling mechanism. Normally I would use a singleton class, but it seems like a subsystem is nothing more than a fancy singleton class under the subsystem wrapper. So we're going to do that. So we're going to create both of those two C++ files. So go ahead and pause the video, create those two classes if you'd like, name them whatever you think is appropriate for you, and then I'll pull up the starter code that you can use to get us up and running. All right, so the header file for the AI spawner, this should be what you get directly out of the generation of the class from within the editor, right? So I haven't added anything to this. I don't plan to add anything to this in this video. This is kind of the basic empty AI spawner header file. So you can double check that that's what yours looks like. And then you get the basic C++ file, which again is very similar to a blueprint where you end up with the begin play, event tick, and the constructor. That's what those three functions are. And we're not doing anything yet with those, right? But we want to go ahead and we want to make that class now and make sure that it compiles cleanly because we're going to build upon that in the subsequent videos. When you open your subsystem, you're not going to have much of anything other than the base class. And so the first thing we did in the subsystem header, so this is the AI spawner subsystem header file, is we added our log category. So this is declaring a log category, and we gave it a name, log AI spawner subsystem. We set its default to log. So this says that by default in the log file, I'm going to show everything of verbose log or above. But this line basically uses a macro that says, hey, I want to have a new log category. I don't want to use log temp. I want to have a log category for this particular area of the system so that I can turn it on and off when I'm debugging. Later, we'll add some structures here. We don't have any yet. This will be auto-generated. We created a very basic, simple blueprint callable function, which is get AI actor from pool, and it returns nothing but a bool. So this is simply a placeholder, right? This is publicly exposed so other classes can access it. And we're going to use it in this video just as a test case. But later on, we'll actually flesh these out and we'll add more functions. But for now, the subsystem only has one accessible function. It is accessible via blueprints. It's called get AI actor from pool. There's two functions that we have overridden. That's why it says override from the parent class. One is the initialization, and the second is the deinitialization. So the subsystem and the engine will automatically create the subsystem upon the world being loaded. What we're doing is we're hooking in to both the initialization and the deinitialization for the purposes of showing you guys how that works and for testing to make sure our system's up and running. So that's the extent of the header file at this point for the subsystem. The C++ file for the subsystem is we have this slightly different macro here, which defines the log category. You'll note that so if I back up, there's a much longer declare the log category here in the header file. and a much shorter define the log category here in the C++ file. So if you haven't created log files before, just sort of copy and paste that exactly off that screen or get it off Google. But that basically allows me to use that log category. So and then I have the three functions, right? So maybe let's do the bool. This is the namespace. So this is the namespace that comes from right here. All right, so this is saying, hey, this is my namespace. And my functions will have that followed by the name of the function here, making sure the parameters are the same and the return type is the same. All we're doing if we ever call get AI actor from pool is we're going to log to our log subsystem at the warning level this text. And then we're going to return true through the bool function. On the initialize, we're going to call the parent initialization first. So typically when I'm creating things like begin play, initialize, I'm in the front curve, I tend to call the super first to let the parent do its work before I do my work. So in this case, when we call initialize or when the engine calls initialize, the parent function will work first and then our logic will follow second. And so all we're doing at this point is again logging to that log file. The AI spawner was initialized and we're going to give it the world name. So here is get the world, which gets the world object, gets the name, which returns a string. We dereference the string, that's what this star does, and then that goes into %ampersand. So this says AI spawner subsystem initialize for world, whatever this name is. Important is that you deinitialize the string here with the star, and they use the %s as the variable placeholder for this. Deinitialize is the opposite. I do my logic first, then I do the parent logic because we're on our way out of the class. So that's it for the C++. Once yours looks like that, let's go ahead and compile it, launch the editor, and then let's see how that looks in game. Okay, so we've compiled our code and we've launched the editor. Hopefully that's working for you as well. First thing I want to do is, so I launched the editor and loaded my default map, which is my 3v3 map. This is how my editor is set up to launch. What I want to do is go to the output file right away. And I'm going to filter to just warning messages because we set some warning messages. And I want to check, and you should as well, that the log spawner subsystem is sending these messages. So the very first thing it did was initialized the untitled world. Then it closed the untitled world and it opened my 3v3 world. So this is showing that the AI spawner subsystem is automatically opening and closing when maps change, right? And so the reason we picked the world subsystem is that it lives for the duration of a map. And that seems to best correlate with the AI that would live on that map, right? So I purposely chose the world subsystem because it'll auto-initiate and deinitialize when I change maps. And when I change maps, I no longer need all the AI logic of the prior map because I've destroyed that map. So I might as well destroy all that AI logic. And when I bring up a new map, I want to be bringing up my new object pool and my new AI spawners. So that's kind of the first step to make sure that those are working. And they are. And then so if we change, I'll leave it filtered to warnings. If we change to our map we're going to be using in this series, and go to our output log, we see that the subsystem was deinitialized for 3v3 and initialized for our new world. So as we switch maps, our subsystem is coming and going. We're getting our log message. So all of that looks good. Now, I haven't really thought about what to do here. So let's create a new folder. And we're just going to call it spawners. This may not be where it lives long term, but at least for now, we're gonna create a new folder called spawners, and we're going to create a new blueprint class. We're going to base that on our AI spawner. So here's our new class that we created in C++ called AI spawner. Its base parent is actor, so we're going to take the AI spawner. And we're going to follow the B underscore AI spawner. That's good enough for now. All right, so we have a new actor called Blueprint AI spawner. And we're going to open that up. And let's see. We will need this stuff later, but we don't need it right now. All right, so begin play, initialize. Let's go with well, let's put it for begin play now. So one of the things I want to do is go has authority, and if it doesn't have authority, I'm going to destroy myself. Okay. There are other ways to do this, but the first thing I said is I'm going to show it to you kind of live, right? So what I'm saying is, okay, if I'm on a client, I don't need this AI spawner. So if this AI spawner spawns on a client, just go ahead and get rid of it. We don't need it. Now we'll make some changes so that it never spawns on the client. But nonetheless, for this video, this works just fine. And if it is on the server, Opcon being in play, we're going to, let's get our AI subsystem. So here you see under our world subsystems, we have our new get AI spawner subsystem. We're going to get that reference, very similar to what we do in other videos with the Lyra gameplay message subsystem. We now have this new subsystem. And we know that we have a get AI actor from pool. And so this is the function that we wrote in C++. It doesn't do anything at this moment, but on server or on authoritative server, we're going to get AI actor from pool, which is going to log a message and return true. And that's sort of it. So we have the basics of our AI spawner. We're going to compile that. I should have saved it too. And I'm going to drag our AI spawner into our level. Just put it about here. So our AI spawner is in the level, and I'm going to basically clear my log. So when I launch this, let's go to editor preferences. That over here. And developer settings, and I'm going to have number of bots to spawn 0. That's all I need to do there. You know what I'm going to do? I'm going to change my default maps and modes, so that's not in here. So for the rest of this series, I'm going to go to my project settings. I'm going to go to maps and modes, and instead of loading 3v3, I'm going to go get our landscape as our default map to load upon launching the editor. All right, so we've cleared our log, and we are set to play standalone. So in play standalone, we're both the server and the client. So we're authoritative as well as the client. So we should get our message. Go ahead and hit play. Now the world subsystem is already up and running, so we won't get another world subsystem message because it's currently running. But in our output log, well, I guess it does redo it. That's good to know. So when you launch in editor, it will reinitialize. And here is the message that we got from our AI spawner when we did on begin play, right? So we did an on begin play and we got that message. So if I have, we need to make that move faster. Now if I have 2 AI spawners, let's put one over here, and let's put another one over here. This is not rocket science. Those are attempts to read the database is what those errors are happening. We go to our output log, we'll see that both AI spawners made the call to request an actor from the object pool. So, all right, so at this point, we have talked through the overall design and objectives. We've created our C++ classes. They're basically empty shells at this moment. We've created our blueprint class that we'll be able to put into the world. And we've checked that the subsystem is initializing and deinitializing properly, and that we can access the subsystem from within the other actor. So that's it for this video. Hopefully, if you're interested, give a like or comment, and we'll try to work through this together. So thanks for watching, and welcome to the new series.